welcome to another coding session. This time we're going to get stuck into a refactor. It's actually a pretty big beast of a refactor, but it's something that I think is really going to help us, help to enable this, which is the way we're going to have aliases for types effectively. I want to think of everything as an identifier. So this is just an identifier that happens to identify a type, whereas this identifier is identifying a value. You could say, it's something that's actually allocated in memory and can be manipulated, whereas this is just identifying a type. And this, my proc, is just an identifier that it's identifying a procedure. So everything's an identifier, that's my idea. If we go into type checking, we can see no, let's not start from there. Let's start from the beginning. At the moment, we have an AST, an abstract syntax tree, made of these nodes, and they have this special data type here. And what I want to do is cut that out. I'm going to put a note here, because in the future we might make directives their own node, but at the moment we'll just put it like this. So the idea is that data types are now just going to be nodes in the AST. They're going to have their own nodes. They're not going to be a special struct or anything. So they're going to have the type. And they're going to take on the same structure as, like this is the structure of nodes in the AST. Like this is the AST here. And this structure here is saying, like we have this identifier, which in this case is probably a pointer to an array. This is identifying a pointer to an array, so we can dereference. So then now we have just an array. We've taken away the pointer part. And then when we index, then we go to an element of the array, which we can then add to a number. So this structure here, we're going to sort of do something very similar for types. And the way we're going to do that is we have this left-hand side primary, right-hand side primary. So we're going to make a type primary as well. Instead of putting untyped there, let's just say that it can be a directive. So let's just see what types can do. You can't negate a type. You can have a directive on the type. You can have a pointer to a type. So those are okay. You can't dereference a type. You can have a link. This would be a link for the type. So this is square brackets. But we'd only allow a number here because we don't have compile time evaluation of expressions. You can't do dot notation on a type. You cannot have a sub-expression or a call. And you can't have, these literals here, and you can't have a null. So you can have those things. But the extra things you can have are the struct type is a valid type, and the procedure type is also a valid type. So we're going to allow that in the type primary. So we also, previously we had this type here, which has kind of been replaced by the type primary, and this data type also. So instead of all these specific type names, that's just identifier now. They're just identifiers. That's the idea. So we can take away these two. And it looks like I was already searching for type, because anywhere we have like type like this, we need to put primary, because they are type primaries now. Here and here, maybe that's it. Yep, I think so. So that's how we're going to restructure the grammar. So in tokenization, well, I guess in tokens, I think this is where we have, a list of data types. We're going to cut that out now. And so then in tokenization here, we'll also get rid of this data type, token type, because there's nothing special about a data type anymore. It's just a token. So now we can get rid of this. Okay, then we can move across to parsing, where there will be a plethora of errors. Then we just basically need to search for anywhere where there's data type, and that needs to be replaced. So this is where we are parsing a type. So it's actually going to be parse primary now, because type is just a primary. I'm just going to put false in here for now, which means that it's going to actually parse a right-hand side primary. Later we really need to refine that because it's going to be able to do all these things a right-hand side primary can do, but it should be limited to a type primary. But just to keep things simple right now, I'm just going to parse a right-hand side primary here and put that in a type node. So this is going to return a node now because there's no such thing as a data type. And then we'll just add it as a child. So generally, the type node is always going to be a child of the identifier. This left-hand side expression, left-hand side expression it would have to be an identifier node. Actually, that's not true. But again, we're just going to keep things simple here. I don't want to think about things too much. There are existing issues with the code for sure, and I don't want to deal with them right now. I just want to refactor. So let's call this node. So this parse type, I'm going to split this out into two procedures. And all this kind of stuff, like, see, this was to do with like indexing, we cut that out. This is going to be the procedure one, so we just want the code specific to the procedure. And also this kind of stuff we can cut out because we're going to parse the procedure type in the context of a primary. The parsing of the primary is going to take care of making all those extra nodes, you know? The nodes for references and indexes and all that sort of stuff will be taken care of. So we have a procedure type node. Parameters type node. So we're just going to change all this to nodes basically. Don't need that length anymore. And this is going to be a node, and I'm actually going to do like a proper parse identifier now. And this is going to be the type node. So this will be parse primary now. False to make it right hand side. We'll improve that later. So the type node becomes a child of the node, and the node becomes a child of the parameters. So it's a little more complex now. We have an identifier node with a type node under it, whereas before we just had the one data type struct, I guess. And this is a type node, and that's parse primary. False. So that's a parse a procedure. Now I want to do the struct. Should be this part of the code. So instead we want to call it a struct. And we do something pretty similar. We do parse identifier. Sorry, I can't remember if I mentioned this. It's kind of important. My plan here is just to get enough of the refactor done that the code compiles. Because it's a huge refactor, it's going to take a long time. So we're just going to get it compiling we're going to have the compiler compiling at the end of this session, and the next session we should be able to clear up all the inevitable errors and maybe even get the aliasing, the type aliasing working. Hopefully we can manage to get that in the next session. I think that's it for this. So now this is struct type. And then when we parse a primary, if we can find that, here's parse primary. So we'll add a keyword case. And then, do you know why my light flickers sometimes? I thought it was a fancy light. And then we're going to switch on the value. And if we find a struct or if we find a proc, then we will parse a struct. Or we will parse a proc. Nothing too groundbreaking there. And we should probably also put default case in here that throws an error. I mean, actually, it should assert here because that should never happen. We're parsing, no, it could happen. It could happen. Someone could put that in there. Okay. All right. I think that's pretty much it for parsing. So let's go to type checking and change all these. So I'm going to make this just, I'm going to take off the data type suffix there. And the reason is that now these identifiers, they're going to store directly the node of the thing they're identifying. Where previously I would get the data type from the value, now I'm going to store the value itself. Or if the identifier is for a type, then I store the type. Because if I'm only storing type nodes, how do I differentiate whether I'm identifying a type or a value? That's kind of the problem. And this here is a bit annoying. This is going to get a bit more complicated. Type value, place all, and that just gets replaced with nothing. So that's kind of better, but there's still more to it. Because that actually needs to be a child. Because like I say, the things that we put into the identifier list, like this is identifying a procedure. It's not identifying a procedure type, it's identifying a procedure. So the root node needs to be the identifier of the procedure, and then the child is the type. So the child of the child is the parameters, and then their children are the individual parameters, and there's the return type. But then also, the parameters are more complicated, because they have their own identifier nodes. So we need to go like this. Doot, 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 doot. Doot, doot. And that's arg0. 1, 2, 3, 4, 5. And then these become the children of those identifier nodes. So this is a real, this is way more complicated. This is why I did, you might remember that in a previous session, I wanted to reduce the amount of procedures we had hard-coded in here, and this is why, because this is, to go through all of those procedures and do that would have been a real pain in the ass. Oh, the value of the identifier should be syscall. Okay. So now, again, we need to like deepen everything by 1. And this doesn't have any parameters, but this procedure itself is a parameter. So it needs to have a a parent, which is its identifier. Just call it thread prop, I don't know. I don't think you ever see that name. And then we'll go like that. Let's search for data type again. Okay, next problem. We can't just do this anymore to get the data type. So what we actually need to do is have like a get type. And then we should have the type node. And then we can check the type node of the value to see if it's a procedure. And then we do our thing. So get rid of that. I think it's like that. I'm going to make these pointers. And then, so actually, no, we need to get the left-hand side. This is the left-hand side node. So maybe I don't need to do that. And we get the type of the left-hand side. So that's the left-hand side type node. And that would be the type of procedure. In which case, we put the left-hand side node in the identifiers. Okay. So that is that, except we don't have a get type. So let's put it here. I'm pretty sure, we'll say node. I'm pretty sure we can amend this later if it's not the case, but I'm pretty sure that the type of a node will always be its last child. So if there are no children, obviously return nil. The default is to return nil. But if we find, actually let's save this. If we find that the last child, so that'll be child count minus 1, is a type, then we return it, basically. So now we need an is type. So this assumes that the node you pass in is a type node. Well, that's the idea, that it should be a type node. Type node dot type equals type. Then we return true, so this is going to return a bool. If it's index or reference, because remember the structure can be like this, but actually with a type node, we can't have dereference. We can have reference. We can have index and reference and type. So if we're looking at one of these index or reference nodes, it could be that we go further down into our children and we find the type. So that's what we'll do. We'll recurse down to the children. Type node children 0. Okay. So I think that's all implemented, and that should work. So now let's go down to here. So we want the type of the procedure. So what we need to do is use our good old get type of the procedure, check how many children it has. If it has 2, use the second child. Good. Very good. I think that's it. Okay, let's move along. You get the type of the left-hand side node. Check if it's for a procedure. If it is, let's check the directive. The procedure becomes the left-hand side node here, and this is the params type node now, and that's the param node, because remember we have within here we have actually identifier nodes, so that value will be the identifier. Yeah, we want to put the identifier node in the identifiers. QQ, so left-hand side type node. And here, here we want to say, so now we change that to if it's nil, so if it hasn't been set yet, then the way to set it is to append. Whoa. To left-hand side node children, like so. I'm going to rename this to get type result, and we also need to use get type, because I want this get type result to assume that it is given a type node. So I'll call this type node, and it will give back a type node, well, a node. So if it finds that it's a call to children, that returns the second child, otherwise it returns itself. Yeah, I think that's still right. I think we'll need to dereference that. So now, because within all of this if statement, we could have added a new type node, we need to do get type again. And if we still find that it's nil, that there is no type of information on the left-hand side, then we throw an error. Otherwise, we want to add to the list of identifiers. This might be a bad idea, but I do think that we want to... Okay, no, we'll leave that for now. I think this is going to cause trouble. Just going to put that there for now, because I think we could be adding things into the identifiers that we shouldn't be. But we haven't seen any problems yet, so let's just leave it. Probably because we have not used structs hardly at all. So we get the type node and the identifier type node, I guess. Identifiers. Identifier type node. Let's call that type names. Call that type name. So that'll be type node and identifier type node. Let's go to, no, let's do that later. Looks hard. So we'll call this expected type node, which is an AST node pointer. So we get the type of that node. This one is already a type node, so we don't need to do get type. But we'll give these more relevant names. Type node result. Expected type node result. Yeah, I think that's all good, but I want to rename this one to something coerced type node, so it's more obvious what we're talking about there. I feel like just calling it data type was not great. And upgrade types. Okay. So we want to get type because this might not exist. So if it does exist, what the hell is this supposed to be? So especially not equals, Jesus. Then we have a directive, and then we need to do get type again. Now we're guaranteed that it will actually, because this type check primary should have added a type node if there was not one there already. But we have to be careful because this one might have gotten overridden, so we can't just keep this. Anyway. Okay, get type. Going to be lots of this get type business. So I guess this is like the LHS type node result. Type node result. Coerced type node. Type names. Cool. It's just a bunch of renaming mostly. So here we want to append type information to the node. So we need a pointer, and what this reminds me actually that what I want to do is put in these in the identifier list all of our base types. So let's do that now. Just like that. So it just means that we've established that it is a type. Bool is a type. And we'll see later how that works. So we have cint, cstring, just going to have to list them all here. F32, F64, I8, I16, I32 and I64, and then I think it's just procedure and string. I think that's all the types. So yeah, then we can just do that. And also here, well, we don't need to reference that one actually, but here we can do the same thing. And that's value. Here again, we're assigning to this node, but now we use this, which we need to dereference. So if the type is index or reference, type of the node, and here just for nicer naming we do that. Ooh, and that is value, and that is value. Okay, get in there, get in there. Right, so this gets a little bit tricky. This is saying take the type information, because we've just type checked the child. This is saying take the type information from the child and give it to me. but I'm also a reference. So the way we do that now is we wrap it in the type in a reference node. I guess we call that just type node. So we're going to create this type node, and the child of it is going to be the type of the child. Which I'm going to put here because, and I want to lift this up because I think that makes more sense. Because here we're checking the child type is a reference. No, if it is a reference, that's bad. At the moment, we're not allowing referencing of references. And I think this is also kind of the child type node because I want to improve this. Give it a bit more of a useful error message, cannot reference type, so that should be the child type because that's what you cannot reference. And we don't need this line, but instead we're going to actually apply this to the node, like so. That's how it works. Okay. Now we do something similar for negation. So I'm going to get the child type. It's saying if it's a reference and an array. I think that's wrong. I think it should be or. So if it's an array or a reference, then we just say cannot negate type. Put that type in there. And in the case of negation, the type doesn't change, right? We just copy the type from the child. So this is just child type node dereferenced. Easy. Okay. Dereference, we'll do something similar. So here we're saying that if the child node is not a reference, that's bad. Because if you're dereferencing, you should be starting with a reference. That makes sense. So cannot dereference type. And here we want to remove the referenceness. So this is a little bit different because instead of wrapping in a reference node, when it comes to the type, it doesn't make sense to say that the type is a reference of a dereference of an array or something. We just say it's the array, right? If we're dereferencing a reference, then it's just whatever we were initially referencing to, that's the type. Which I think means we just need to get the child of that type, the reference. This is the reference type. So whatever its child is should be what it was referencing. And I think that should work. Let's see. Index, this one I think is going to be a pain in the ass. Okay, let's see. Again, I think we need to get the child type node. And if that is a reference, then we do this stuff. Now, this is a pointer to a node which is a child of this. And here we're clobbering that. So I'm going to dereference this so this becomes a copy. And then hopefully that should mean that it does not cause that issue. So here again we're dereferencing. It's like the same as this. Except we're talking about this node that we're doing it to. So whatever it was referencing becomes its type. I think that's right. And the child node becomes a child of this guy. But I think we want to do that first. Because remember when I did my get type logic, I was assuming that the type is always the last child. So let's put the child node in first, then the type node. Right. Now we need to figure out the type information for this node. And I think that depends on what we were referencing, because we could have been referencing an array, or we could have been referencing just an individual element of the array. And why does that make a difference? I had it in my head that they should make a difference. Well, we're indexing into it. Yeah, we're indexing into whatever it is, so we should end up with just an element. The type should be just an element. So I think we need to get the child type again. So now we should have this if it was auto dereferencing. So this should be either an array or the element. I know this is probably a bit confusing, but I kind of have to race through this. So if the type is index, which, yeah, it's not great. It actually means that the type is an array. Then we want to set the type of this current node to be the child of that type, which would be the type of an element of the array. Whereas if it was not an array, then we just grab the thing directly. I think that's going to work. Let's see. Let's see what happens. And the boundless, where is the boundless stored? The boundless is stored on the reference node. And I think we kind of want it to be on this node as well. Do we need it to be on that node? Because this reference node is kind of getting buried down now. I'm not sure if this is best. But let's do this. Let's just say if we get the type of the node, that directive should equal that directive. So this child node, that's the reference type, right? So that one should have the directive on it if it's boundless. So we'll just put that onto this current node's type node. Then we should be able to just do this. I think, and that should work. We need to get the length. We need to get the length. So again, if this child, if we're dealing with an array, then it's like the array's first child is the expression, and we know that for types, the expression is just a number, so we can just grab the value. So we can do that. And if it's not an array, then we just say 1. I think that's right. Okay, good enough for now. Sorry, we're racing. I know we're racing. Oh, that should be child type node. Okay. So this doesn't make sense anymore because the node could have type information as a child. what we're trying to say here is, are we dealing with a struct member? And we know it's a struct member if, like this is a struct member because the child should be an identifier. This is also a member, so the child is an identifier. So if we have a child and that first child is an identifier, that means we're dealing with a struct member. So I'm going to say, well, let's get the reference. Child deno. Put that in there. And then child type node is get type because, whoops, because this call here should have got the type information for it. And which should be a struct. Actually, that's just node. And then, so then we want to assign that type information. Node dot to this node? Yeah, to this node, it looks like. So we get the type of the member node. That needs to be a pointer. Okay. I think that's looking good. And here, and if we're not talking about all the struct stuff, then we just check like, okay, is it in the identifiers? And if it is, we also need to get type of the identifier and put it in. And here is just like sort of hard coded, you know, like in this case, for all these things, we know what the type is going to be. Like this one's going to be string. So it'll be type equals type and then value equals string. And the same for all these. That, so it looks like that. We do need to handle the type case. Although we can just say nothing to do. Do we need to handle the type case? I'm really curious if it goes there. Just put a to-do there just in case I don't notice that happening. Okay, so now we're going to type check a call. We check if the procedure exists. I do want to put an extra check in here. Because we'll get the type of the procedure. And I just want to double check that that is actually a procedure. Right? That's a nice thing to know. So identifier blah does not refer to a procedure. So this is the type node, which is a child of type node. And so that's all right, I think. We already have param node here, so I'm going to call this param node from type, and we need to get the type of it. This refactor is definitely making things more complicated, but I think it has a lot of benefits too. Generally, I'm against complicated unless it really has a payoff. So this would be the procedure type node that we're adding here. And then we want to override the value of it, so just say get the type of the node and override the value of it, like so. Okay, okay, get in there, get in there. I think this part is easy. It's a bit weird. Like, I don't know how necessary this is, but I feel like you should only do this if it's inline. Kind of makes more sense to me. For this one, I want to get the identifier node. First, I want to check if it's a type. Because if it's a type, I think we do want to copy it down to child, types. Why not? We bring them all with us. Any types we declare, I don't see the harm in that. Otherwise, we get the type of the identifier node. Hopefully at this point, it will have a type. If it doesn't, we'll get an error and we can deal with it. Okay, we're getting into utility functions now. So AST node. So here we're kind of saying like if A is nil or B is nil, and that should be a B. And I guess we should first check, if A is nil and B is nil. Do we need to check that? Like if we come in here, A is nil, then we just return B, which is nil, which is what I was going to return here anyway. So I don't think that's actually needed. Next thing I think is to check that the types are equal. Now this gets a little bit trickier. I think we might need to do this in two separate things. So, and it's only really if we're dealing with, it should only be a reference thing. I'm not sure if that's necessary to do that, but so if A is boundless and B is not boundless, you know what, maybe I'll just leave this for now. We'll get an error, and then I think it might be easier to deal with it when we see the error actually. Might make more sense. This all stays the same. I do think this is kind of like if this is really what we're talking about. If the values are different, then if we're dealing with a type, then we do all this stuff. I mean, I think the type is the only thing that actually has a value, but just to be kind of defensive, I'm going to say, like, for anything else, just say false if the values are different. I don't think that should ever happen, but yeah, like I said, just being extra defensive. So we know the values are different. Okay, so that does that stuff. Length of the children are different, yes. I don't want to create separate lists anymore. I don't want to create a new list of children, we'll just keep it simpler than that. So we're just going to do this. But that will need to be pointers that we pass in. So AST node is a type node. Now that we have this more complex structure, what we're saying here is that it's an array. And if it's an array, it should be children, the first child. That first child is the expression of the array, which we know is always a number node. So we just grab the value from it. So we don't need this. And I think we just return, but we also recurse. There might be some other stuff to prepend with. For references, we should also return just with a hat on the start and also recurse. Type node.value, but we want to prefix actually. Let's do this so it can work for all of these nodes. If there is a directive, then we want that directive followed by a space, otherwise just an empty string. And let's just put that at the front of all of these. So this last one will just be like prefix name. Well, prefix type node value. Like that. Yeah, I think that's right. These are new ones that we made. Okay. Upgrade types. So this is like the new type node that we're upgrading to. Kind of want to change this logic a little bit. I don't like it that much. So if the node is a type node, and I actually kind of want to say if it satisfies one of these, I feel like that's easier to understand. If it satisfies one of those, then we do something and we recurse. Yeah. So how do we do this? I think basically we set that to be that. So we just override that node with this node. Yeah, we've got a bunch of errors, but let's push forward. Let's get all the data typeness out of here first. And then we'll get back to that. So this is basically just a reference node. Unknown reference node. No, I guess. I guess we'll call it, we always use it just for types. Unknown reference type node. Yeah, that'll do. Okay, this here is similar to what we did up here. Be this kind of logic. But here we're saying where it's not a procedure. So let's just put a continue in there and put that there. And then there should be another thing down here that's talking about when it is a procedure. This one, so we put that in like that. Nice. Okay, looks like we want the type node. Since we're in generation, we can just always assume that type nodes exist. Everything should be typed. LHS type node, params type node. operand node, which has an identifier. This needs to be get type. Which kind of reminds me that I think I want to just like change everything to pointers. I think that's going to be easier. Okay. We're going to find data type. Okay. So we'll make them pointers, and then we can just do get type. Like so, and it's probably a few like that. Child node, get type. So the child node needs to be a pointer. That needs to be a pointer now. Here we use this like 3 times. So let's do get type with the expression node and put that in here. Get type. Whole lot of get type. So here is where we're saying like, do we have a right-hand side node or not? I think we need to make an actual if statement here. First case can be when there's not a right-hand side. Second case when there is. So this is for an assignment where we're generating an assignment. So if there is a right-hand side node, it's pretty easy. We just pass it in. If there isn't, then we want to create this node, this null node, which has the type information of the left-hand side. And the way we do that now is to add, oh, we have get type of the left-hand side here. So let's do that. And now we can put that as a child, go like that, and make a pointer out of that. I think, yeah, so I think that does the same thing. It's a null node with the type information from the left-hand side. And it needs that type information so we know how much, how big the thing we're setting to null is, because we need to know how many bytes to set. Okay. No surprise for guessing what to do here. We'll call this the type node result. Get type again. And again. This is the operand type node and the result type node. All of these, we just want to take out the data from the name. And we also need to change these to be value, like that. There's going to be a few procedures that we need to change this in. I'm going to copy this because I think it'd be handy. Type node, type node. Hopefully that's enough to solve that. Okay. In here, I think we're going to need the type node a lot. So let's get the type node. So that's going to be there and there and there. I guess this needs to be a pointer. It's not always so simple. I think we need to do something like this, because this type node might not be maybe in this case it always is actually, but I don't know, just gonna be safe, because we have like this multi-node structure to a type. I just want to make sure we get the value from the actual type node. Yeah, like I say, I think in this case it's actually not an issue. But I'm going to do it anyway. Okay, type node, type node. What else we got here? This I've been meaning to do, like, I think we can just do byte size of type node context. Here, let's get the expression node, and then the expression type node. So here we want the expression type node. Here we want the expression node. This is the type node. The length again, this is type node. The length again changes how we get it. How do we do it here? I think we just copy this. Something like that. So that was looking at the child type node. But this is the type node, the index node. For boundless. Yeah, that's how we did it. Okay, so we need to get the child type node. Yeah, I think that works. Then we set this length like so. Okay. This is where I was saying we need to have this get. But in the case of a procedure, I don't know. I'm just going to use type node.value here, but it might throw an error at some point. This again is the same condition, you know, for the here. It's saying like, hey, do we have an identifier child? Except here we know we would have at least one children because we would have at least the type information as a child. So I don't think we need to do that. In fact, we could probably do probably just straight up get the child node like that, and then we can use it there as well. And then we get the type from it, and that will contain member nodes, which we can check and offset by. That'll need to be a pointer. Alrighty. When we have a number node, I'm pretty sure, yeah, in this case, definitely we can just use the value. Because number node is like, this could not be a reference or something. This is the number. Okay, so we need a type node. Like so. Type node, type node, type node, params, type node, return type node. This is the type node again. This is the param node, which we need to get the type of. This is a pointer already, so we don't need to do that. Type node. Here we have the param node again, so we do this from type business. But anywhere we use it, probably we need to use get type, because that's what we were previously expecting. Like so, which means it needs to be a pointer. Okay, get in there. We're over an hour in. So this is a monster refactor. We have to do the same thing here. Get type, return type node equals null. I think that's right. Type node. And it's pointer already. Okay. We're getting down into the utility functions now. Okay. And these ones you don't really need to do anything. Here we need to use the value. And here we're making sure it's not a reference, but because of the new structure, if we've managed to determine that it's a float type, then it must not be a reference because it's a type node, not a reference node. So we can just take that off. Okay, get in there. Get type of the node. That's all we need to do there. Again, we don't need to have this reference check. Type node. This is all pretty much the same, don't need that. Okay, now we're just down here, byte size of, type node. So if it's a reference, do address size. If it's a struct, we go through the member nodes and sum up the sizes of their types. So that needs to be a pointer. And then we just go to these data sizes. This length is really if we're looking at an index node, then we want to recurse. And multiply the result by, so we need to get the expression node, which is the first child. And we know it's a number, so we can just get the value. So I think it's like that. We don't need this anymore because of that. Okay. Now we just need to address all these errors, which, yeah, I think a lot of them are going to be like something needs to be a pointer. That one needs to be a pointer because I changed it so that everything takes pointers now. This param node, let's make that a pointer. Yeah, make that a pointer. It's all pointer business. These are pointers. Child node should be a pointer. That should be a pointer. So should that. This should take a pointer. These should be pointers. Oh yeah, we need a get type value. Let's get back to that. These should all be pointers. That needs a colon. Should be a pointer. Still have some errors. Oh yeah, that was those ones. Param node should be a pointer. Param node should be a pointer. It's all pointers. Param node from type, that should be a pointer. So should that. Make these pointers. And child node should be a pointer. So we need to get type value. Let's put it in here in these utilities, like here, which I guess returns a string. And I think it's pretty similar to like isType. So if we have a type node, we get the value. Default is nothing. If we have this, then we recurse in. I think that's it. Yeah, I think that's it. So this file should be pretty happy now. Yeah, those should not be complaining. I think they're fine. It's just the IDE. Okay, so here we get from the identifiers the bool, like so. And there should be another one for the for. Here it is. Not really that necessary, but I'm going to use the most relevant context. Param node is not a pointer. It doesn't need to be in this case. Okay. This one I need to dereference. This one is an I64, which we can get from the identifiers. Oh, that should be member node.value. Oh, that should be value. And what else do we have here? Let's type, that should be a pointer. And that should return a pointer. Have we managed to get to, no, we do still have errors in parsing. Parse struct type. Oh, this should return just not a pointer to a node, just a node. And that one too, I guess. And what's this? This has parse type, so it should be parse primary, and we'll just call it a right-hand side for now. Okay, so it fails, but it compiles. That was our goal. So We got this far. Probably it's a whole mess that we need to clean up, but it's okay. It's okay. We're sorted for now. Yeah, sorry, I feel like there's not really much payoff at the end of this one. The next one should have a payoff, but it's just such a long thing to do. I was just like, you know, I was really grinding to get all this sorted. Let's see how well I've done it. The next episode will be telling how many bugs do we have to fix. Yeah, but look, it's been an hour 15, so it's plenty. Enough for today. Okay, thanks for stopping by. Come by for the next one to see the conclusion. Ciao for now.